All right, continuing on with conjugated dienes, let's look at the electrophilic addition to 1,2 or to 1,3 dienes. We're going to look at 1,2 versus 1,4 addition. We'll start with a little, hey, let's remember about organic 1. Recall, when you have a double bond, and you add HBr, HCl, or HI to that double bond, that it follows Markovnikov's rule. The carbon with more hydrogens gets the hydrogen, the other carbon, the more substituted carbon, gets the halogen. All right, and Markovnikov's rule works. The carbon with more hydrogens gets the hydrogen because the first thing that happens is the double bond, the pi bond, attacks that hydrogen, so the hydrogen adds first. If the hydrogen adds to the first carbon here, then we get a secondary carbocation. If the hydrogen were going to add to this carbon over here, we'd end up with a primary carbocation. Secondary carbocation is more stable, therefore the hydrogen goes on the carbon with more hydrogens because that generates the more stable carbocation. So, let's now look at the situation where we have a conjugated double bond. So we have double bond, single bond, double bond here, and the pi bond will attack the hydrogen, given the Br minus. And the question is, which of these two carbons will get the hydrogen? Well, it still follows Markovnikov's rule, because if this carbon over here got the hydrogen, then we would end up with a primary carbocation. So it's the end carbon here. The carbon with more hydrogens gets the hydrogen to make the more stable carbocation. And note, this isn't just a secondary carbocation, this is an allylic carbocation. Allylic carbocations are even more stable. All right, so once we have the secondary carbocation, Br minus will attack that carbocation, and we will put the bromine on this carbon right here. We'll call this end carbon of the double bond that reacts carbon number 1, so this is carbon number 2. Carbon number 1 gets the hydrogen, carbon number 2 gets the bromine. We call this 1,2 addition. However, if you recall from previous videos on resonance, that a allylic carbocation has a resonance form. So once this carbocation is made, realize that once you have generated carbocation, we have resonance forms, and so it's not this in solution, it's not this in solution, it's some combination. The resonance hybrid is what's in solution. So when this Br minus here is looking at this beast, even though we draw with resonance forms, it's seeing a positive charge on this second carbon. Note this carbon over here got the hydrogen. This is carbon 1. It's seeing partial positive charge on carbon 2. It's also seeing partial positive charge on carbon number 4. This is what the resonance hybrid looks like, or you can look at it as the combination of these two resonance forms. So we get 1,2 addition when the bromine attacks the first carbon here, this partial positive, or the bromine can attack the second carbon, since it's also positively charged. The bromide can attack that, and so that's 1, 2, 3, 4. We call that 1,4 addition. Which means if you take this conjugated diene here, 1,3-butadiene, react with HBr, you will get both of these two products. You'll get both the 1,2 addition product and the 1,4 addition product. Okay. All right. So as we continue on, why not this? Why not anti-Markovnikov? When the double bond attacks this hydrogen right here, why doesn't this carbon get the hydrogen and this one become the carbocation? Because no, that's a primary carbocation and there's no resonance here. This is not allylic. For this to be allylic, the double bond would have to be right here. It's not. It's over here. So this is not an allylic carbocation. It's not secondary. This is just a plain old ordinary primary carbocation, and that's just not stable enough to form. So you will not get the anti-Markovnikov product. So working through some examples here, if you have this cyclohexadiene with these two methyl groups on it and react it with HBr, we see that since it's symmetric, it doesn't matter which double bond we choose. Let's choose the top one to attack the hydrogen. So where is the hydrogen going to go? Will it go on this carbon or this carbon? Note if the hydrogen goes on this carbon, it would make an allylic carbocation. If the hydrogen went on this carbon over here, it'll make just a secondary carbocation. So here are our two possible products. The hydrogen goes on this carbon of where the double bond was to make an allylic carbocation, or the hydrogen goes here to make this just plain old secondary. Well, which is more stable? An allylic system, or that is also a, note this is still a secondary carbon as part of an allylic system, or just a normal secondary carbon? Well, the secondary carbon out of the allylic system is more stable than just a regular secondary carbon, so this will be our only carbocation product. However, it's still an allylic system, so it has resonance. This positive charge over here, we can move the double bond to this position and put the positive charge down here. We have this resonance structures here. So the bromine can either go here from our first resonance form of the carbocation, the one we generated first and wrote that resonance form, or it can add here to this resonance form. We would get these two products with hydrobromination of a conjugated diene. All right. Cool. And the interesting thing is we can actually control which carbon, which resonance form, or basically which carbon of the resonance hybrid is more likely to get attacked. Because when we look at this, when we look at this conjugated diene attacking HBr, we noted we could get the 1,2 addition or the 1,4 addition. But it turns out if we're at low temperatures, we make the reaction temperature really low, like at minus 80 degrees Celsius, it turns out 80% of the product is going to be the 1,2 addition, 40% will be 1,4. However, if we do it at high temperatures, like 40 degrees Celsius, we find out that now 80% of the product is the 1,4, only 20% is the 1,2. So we can switch those numbers. If you want mainly 1,2 product, run the reaction at low temperature. If you might want mainly 1,4 product, run the reaction at higher temperature. Now, why is this? Well, let's look at a good old-fashioned potential energy versus reaction progress diagram. Note, here's our two reactants, our conjugated diene and our HBr. They have to overcome some sort of activation energy, and it forms the resonance hybrid here. But note, this carbon over here is the one that gets the hydrogen. So as this carbon-hydrogen bond is forming, this hydrogen-bromine bond is breaking. Those two are happening at the same time. We're forming a bond between this carbon and this hydrogen. At the same time, we're breaking the bond between this hydrogen and this bromine, which means at the time this bond is formed, the bromine is kind of hanging around this area. When you look at the situation, the bromide ion now is probably hanging pretty close to carbon number 2 because it gave its hydrogen to carbon number 1. So it's probably easier to attack carbon number 2 versus having to swim through the solvent down here to get carbon number 4. Because of that, because this bromide doesn't have to fight very much solvent to get to carbon number 2, this reaction happens faster. It has a lower activation energy. It takes less energy for this bromide to just attack the partial positive charge of the carbon right here, the second carbon, because it's closer to it. And so it will form the 1,2 product. However, when we look at the bromide trying to tack this carbon down here, it's got it takes more energy to get down there, which means we have a higher activation energy, which means that reaction is slower. However, when we look at the product, we note that for the 1,2 product, the double bond is at an end. That's just a mono-substituted double bond. Or for the 1,4 product, the double bond's in the middle. That's a di-substituted double bond. And recall that a di-substituted double bond is more stable than a mono-substituted double bond. So the 1,4 product is more stable than the 1,2. So the 1,2 reaction, 1,2 addition happens faster, but makes a less stable product. 1,4 happens slower, but makes a more stable product. 1,2 makes the less stable product. 1,4 makes the more stable product. But it's a slower reaction. So with temperatures, if we keep it at a low temperature means we might not have as much activation energy to overcome this higher hurdle here, which means we're going to emphasize this lower activation energy, the faster made product. High temperatures, we've got enough energy to overcome the activation energy, no problems anymore, so then we're going to get more of the more stable product. All right. So all of that is summarized in these right down here. Since the hydrogen was added to the end carbon, bromide is closer to C2, takes less energy, lower activation energy to make the 1,2 product. However, the 1,4 product is more stable. So if you give it time, you will get more of that 1,4 product. Or if you raise the temperature, so this bromine it's easier to get over here, it's moving faster, can go over here. Raise the temperature, you can overcome the activation energy barrier to make the 1,4 product. Because the 1,2 addition product happens faster, we call that the kinetic product. The 1,4 product happens slower, but it's a more stable product. We call it the thermodynamic product. And this is something we see throughout organic chemistry synthesis problems. Lower temperatures favor the kinetic product. High temperatures favor the more stable thermodynamic product. All right. We will continue our next video with one of my favorite named reactions, the Diels-Alder.